Behold, you have entered Mr. Vaughn's classroom, a mystical realm where math is made easy.
Welcome back to Mr. Vaughn's classroom, where math is made easy. Before we get started on the video, I'd like to ask you to please go ahead and hit the subscribe button, give this video a thumbs up, and engage with a comment below. In this video, we're looking at Unit 3 on Similarity, Lesson 7, Reasoning about Similarity with Transformations. So the learning goal in this lesson is going to be to describe similar triangles. We have one learning target, and this says that I know the relationships between corresponding sides and angles in similar triangles. So for glossary terms, we're going to start out with similar. One figure is similar to another if there is a sequence of rigid motions and dilations that takes the first figure on to the second. So if we look at the diagram on the right, triangle A prime, B prime, C prime, which is the green triangle, is similar to triangle ABC, which is the blue triangle. Because a rotation with center B, so that turns the blue triangle into the red triangle, followed by a dilation with center P takes ABC to A prime, B prime, C prime. So we're taking that blue triangle, we're rotating it around point B to turn it into the red triangle, and then we're dilating it using point P as the center to grow it from the red triangle to the green triangle. So the blue triangle and the green triangle are going to be similar because their angles are going to be the same. They're simply changing their side lengths by multiplying by a scaling factor. Now that we're done with the introduction, let's go ahead and take a look at the practice problems.
I'm once again asking you to solve this equation, and don't tell me we can't afford to get to the answer.
Practice problem number 1. Sketch a figure that is similar to this figure. Label side and angle measures. So the key word here is similar. So we need to remember that similar means the angles stay the same, but side lengths are multiplied by a scaling factor. So in this case, we could use any scaling factor we want. Just for ease, let's use 1/2. So if we scale by 1/2, then 12 times 1/2 equals 6. So we're going to draw the exact same shape, only this time, instead of every side length being 12, we're going to make every side length 6. So we'll label the side lengths as being 6. We'll label the 30-degree angles staying the same. And we will label the 150-degree angles staying the same. And now we've created a similar figure. Now, we could have multiplied by any scaling factor for the side lengths. We could have multiplied by 2 and made it bigger so that the side lengths were 24. We could have multiplied by 1/3 and every side length would have been 4. You could choose any scaling factor you want, as long as you multiply every side length by that same scaling factor and you make sure you leave the angles the same, because that is what makes it similar. Same angles, the side lengths multiplied by a scaling factor. I hope this helps you make sense of things, but if you do still have any questions, feel free to leave a comment below.
Here we go, folks. We've got a real barn burner of a math problem on our hands today. Let's see how this equation plays out.
Practice problem number 2. Write 2 different sequences of transformations that would show that triangles ABC and AED are similar. The length of AC is 6 units. So, remember that the angles are going to stay the same. Now, the first thing I want to do is identify which side lengths are going to be connected to each other, which ones are going to correlate. So, if I look at DE, that is going to correlate with BC. If I look at AE, that correlates with AB. And then finally, AD correlates with AC. So what we can tell, my correlating side lengths are 2 and 4, 4 and 8, and 3 and 6. They tell us right here. So this means my scaling factors is either multiplying by 2 to go from the small triangle to the big triangle, or 1/2 to go from the big triangle to the small triangle. So if they want 2 different sequences, first, let's go from ABC to AED. So dilate ABC using A as the center by a scale factor of 1/2. That will shrink this big triangle down and it'll create this smaller red triangle. Once we dilate it, we now need to reflect across AD to place on top of AED. So we're just going to reflect it down, and now I end up right on top of AED. So this is one method. Now let's do a different. This time we're going to go the opposite direction. We're going to go from the small triangle to the large triangle. So we are going to dilate AED using A as the center by a scale factor of 2. This is now going to create a larger triangle and then we can reflect across AC. To place on top of A, B, C. So I'm going to reflect this across here, and I'll end up laying it directly on top of ABC. So this is two different sequences, but both of them will accomplish showing that triangles ABC and AED are similar. Their angles are the same. It's just that ABC is twice as large as AED. So I can either scale factor the small one by 2 to turn it into the larger one, or I can scale factor the larger one by 1/2 to turn it into the smaller one. I hope this explanation helps make sense to you, but if you do still have any questions, feel free to leave a comment below.
We're going to have so much winning, you'll get tired of winning. You're going to get tired of solving all these fantastic problems.
Practice problem number 3. This will be our last practice problem in Lesson 7. Select all figures which are similar to parallelogram P. So let's think about what we're looking for. If we want them to be similar, then we need our angles to be the same. That means opposite angles need to be 130 degrees and 50 degrees. Our sides are all the same, and they need to be multiplied by a scale factor. So let's go through and look. If I look at figure A, I have opposite angles of 130 and 50. That's exactly what I needed. All of my sides are the same. That's our second point. And they need to be multiplied by a scale factor. Well, I can scale from 5 to 5 if I multiply by 1. So figure A is similar. Now let's look at figure B. First thing I need, opposite angles of 130 and 50. That's our first point. Second, I need all the sides to be the same, and they're all 3. Last thing, I need them to be multiplied by a scale factor. Well, I can go from 5 to 3 if I multiply by 3/5. This hits all 3 of our points. So figure B is similar to the original figure. Now let's look at figure C. We need opposite angles of 130 and 50. This has angles of 135 and 45. So this has wrong angles. We can stop looking right there. If it doesn't have the same opposite angles, we know right away it's not similar. Figure D. I need opposite angles of 130 and 50. We do have that. Our second feature is that we need all the sides to be the same. And they're not. I have opposite sides of 3 and opposite sides of 5. Sides not the same. We know that it's not similar. And then figure E, I need opposite angles of 130 and 50. But I don't have that here. I do have 2 angles of 130 and 2 angles of 50, but they're not the right opposite angles. So we have the wrong angles. So we can get rid of figure E. So the only shapes that are similar to the original are figure A and figure B. It meets all 3 of our criteria. The opposite angles are 130 and 50. The side lengths are all the same, and we can arrive at the new side lengths if we multiply the original by a scale factor. In figure A, that scale factor was 1, and in figure B, that scale factor was 3/5. I hope this makes sense to you. If you do still have any questions, please leave a comment below. Now let's go review our learning targets before we finish up this video. So we had one learning target here in Unit 3, Lesson 7, and that was for you to know the relationships between corresponding sides and angles in similar triangles. Now, we used different shapes, but it doesn't really matter on the shape whether it's a triangle or a parallelogram. What makes figures similar is that their angles are the same and their corresponding sides can be found by multiplying by a scale factor. And that scale factor could even include 1. So if I have the same exact angles and the same exact sides, then yes, we are similar. We just also happen to be congruent at that point. But the difference between similar and congruent is that with similar figures, you don't necessarily have to have the same side lengths, so similar is not necessarily congruent. I hope this makes sense to you. If you do still have any questions, please feel free to leave a comment below. One thing I would like to mention is that if you look in the description below the video, I have included links to websites where I'm offering one-on-one tutoring sessions. So if that is something you're interested in, please go ahead and check those out. On the screen, if you did find this video helpful, in the bottom left, you should see another video of mine that YouTube is recommending. In the bottom right, you should see a subscription button for the channel. It really would help out if you would subscribe to the channel. Give this video a thumbs up, engage with a comment below, and I look forward to seeing you in the next lesson.